and Professor Corso right now is an associate professor at the University of Michigan, Ann Arbor. And yeah, I'm lucky. Professor Corso is a kind of long-time friend of mine, and due to his relationship with my previous PhD advisor, Dr. Sun Zhu. And Professor Corso has numerous awards, which you can see from the flyer, so I will not present here. And today, we are very glad to have him to present a very wonderful work. And besides, he has a startup right now. I think he's recruiting. So if you are interested after the talk, you can chat with Professor Corso. Okay, without further introducing. So yeah, let's welcome Professor Corso.
Thank you, Professor Wu. It's a pleasure to be here. Yeah, I'm happy to give a presentation about my work in computer vision. So my work has really spanned a few different topics in computer vision over the last 10 or 15 years. But one theme throughout has been the notion of segmentation, kind of pulling out specific elements from images and video. And when looking through my work, I guess I arrived at this general notion that segmentation can be interpreted as a selection problem, right? So intrinsically, segmentation is not well posed, right? So if you look at an image or a video, there are many possible segmentations that you could pull out from it. And so one needs some further guidance or loss or objective function to actually realize what you should pull out. And so I think of that process as selection among plausible segmentations. And we'll go through that under the guise of a few different works over the last decade for you, including some work that's not even yet published. So, right, so I'm still sort of working on this. It's a good problem. I should mention that most of this work is done by my current and past students, Chenliang Xu, Brent Griffin, Tom Yan, and Luei Zhou, who are now professors at Rochester and Texas, and he's a research scientist at Michigan, and Luei is going to be on the job market in a couple of years for faculty or something like that. So, and indeed, I am not only a professor, but I wear a second hat as co-founder and CEO of Voxel 51, which intends to become the developer platform for video understanding as a service. And we are hiring about 10 people of the engineering ilk in the next 3 to 6 months. So I'll have some more information about that later. Before I go on to the slides, so if you have questions at any point, you should just raise your hand and speak up. I'm not here to lecture to you as much as I'd like to talk to you. So if anything's not clear, just let me know. Or if you have some debating comments as well, you can try to derail me. That's fine. I've been doing this for a long time. It's okay. So let's begin with me asking you some questions. Find the nearest monitor in this well-equipped room and answer me if you can tell me what this is an image of. Well, I'll tell you the mechanics. So this was a photo, actually the first frame of a video, that was sent through a segmentation method. And it is outputting a set of regions that have each been randomly colored. Can you tell me what the content of the original video frame was? You think you see a tree. Anyone else think they see other things? A dog, maybe? I see a dog. Let's answer simpler questions. Is it indoors or outdoors? What was outdoors? Indoors. Ah, see. Right? So this is a segmentation. At the time, it was a sort of state-of-the-art segmentation. It wasn't trained by anything. It was bottom-up RGB, maybe plus optical flow segmentation. You can't really find that much from this resolution or this layer. How about now? Does it help a little bit more? Indoor or outdoor? Indoor. Okay, so now you got it's indoor. Is there a dog? Okay. What else might there be? A kid. Okay. So now let's see if you can figure it out a little more. Is it a dog? Yeah, it's a toy, right? All right, so you guys are all really smart, at least in terms of seeing things. No one probably walked into a wall on the way here. Okay, correct me if I'm wrong, right? But you're all at least, I would say, 18 years old, maybe almost. So there you go. Maybe at least 18, maybe older. You've been seeing about 30 frames per second, about 15 hours a day for the last, say, just 20 years. You can do the math. That's a lot of frames. You've seen a lot of data. And you're able to make sort of decisions about what we're seeing based on all of that background. But in this segmentation, before there was motion, before I showed you the pixels, you were mostly wrong. There were some things that were correct, right? So eventually, at some point you got indoor, you kept calling this a dog, right? It's not wrong. It looked like a dog from the segmentation, but we need some more information from the plausible segmentations to pull out what's actually happening. Okay, so we need to select it more. But there is rich information in segmentations. Maybe I'll give you another test. Can you tell what this is? A what? A rainbow? Well, it is very colorful. Yeah. This was my son's art project last year. Yeah, right, so there is rich information there, but it's still not clear what we should be pulling out, like what we should be selecting as the output of the system, right? So that is, these are intended to give you cause that what I'm saying is reasonable, right? So, there are many possible inferences we can make from such video, but pulling out the right thing is the challenge here. Okay, so these are all of those over-segmentations, if you want to call them that, are outputted from one of a class of methods that I would call bottom-up video segmentation. In this type of method, you have a spatial image, okay, and it's going to repeat in time or go across time. Let's interpret that image as a space-time graph or a lattice. Okay, so every pixel in every frame becomes a node in that lattice, and they get replicated and connected to their nearest 6 neighbors in time. Okay, and so this is our space-time graph. Our goal in bottom-up video segmentation is, based on the features we can extract at those individual nodes, say just RGB, or if you want to even go simpler, just grayscale, we want to color that graph so that nodes that belong in the same group, according to some criteria, get colored by the same color and then get grouped together. As we coarsen the graph, they get replaced by single nodes. And so we have this hierarchical interpretation of what we see. Okay, and here's another example output on a fairly high, fast-moving video. We go at coarse levels. This is the 3rd layer of a graph. This is the 9th layer. And the top right is the 13th layer. So in typical videos, even HD videos, you'd get on the order of 18 to 20 layers maximum, with the lowest layer being all of the pixels or voxels in that video, and the top layer being just a few regions. The more important thing to point out, well, before I get there, let me just give you another example here. So this is a much simpler video than the one you just saw. Segmentation at a lower level, medium level, and a higher level. The more important thing to point out is that various structures or things we might care about, in this case the individuals, we might want to count the number of individuals or measure whether or not they're holding the canoes appropriately or detect and track the canoes and so on. Various structures are popping out at different levels. Right? So the best time we get this guy in the yellow jacket is somewhere in the middle, but nowhere do we actually get him in totality, right? So we just get him in 2 segments. So we have to figure out that we should merge those together if we want to get all the people, for example. But in no single layer do all of the people come out as a group, either individually or as a collection. Right? This person is good at the coarser layer as one unit, segmentation. And this person is never grouped he's always mixed with other people, and so we get a lower level, which is the only time we can segment out his hand and his arm. Otherwise, it's grouped with the background. Right? So this is a challenge. So we want to figure out how to select among the plausible segmentations which is the one we care about the most. Okay? This happens beyond video. This is some work I did in medical imaging around maybe 10 years ago. So these are 3 sequences of a multi-sequence MRI scan. Okay, so the T1, T2, sorry, these are 2 sequences of the sequence. There are usually 3 or 4 that we're going to work with. These are just different sort of parameters on the acquisition. These are for brain tumor cases. Okay, so this is glioblastoma multiforme. What you see in the T1 example, in the bottom right of that, is the actual tumor tissue. So this elliptical shaped thing is tumor, but the white part of it is the actual tumor tissue. That means that the tumor cells have broken the blood-brain barrier, and they are what's called enhancing. So that's what the white part is what we see as enhancing on this scan, T1. The dark parts on the T1, those are actually dead tissue. So that's the brain that's been killed by the tumor, and the tumor that's growing so fast that it's killing itself. Okay? In the T2 scan, that's going to be reacting to swelling or water in the brain. And so all of this gray area you see in the bottom right is the edema, or the swelling in the brain. So it's been said that edema is a predictor of tumor growth. The more edema you have, the more the brain's reacting to it, the faster the tumor is going to grow. So if we could quantify not only the volume of the tumor, dead and live cells, as well as the volume of the edema, then we could predict how fast the tumor may grow. Okay, to do that, we need to segment it out. But in these segmentations, nowhere do we actually get just the tumor. We always get the tumor. This is the dead cells with the active cells, the orange and the blue in layer 7. Nowhere do we get just the tumor as one region. We do get the edema as one region in 9 and 10, actually. Even 9, 10, maybe 11. Right? But we still have to work on selecting out which cell, which layer, or which voxels are our goal. Okay? So those are some motivations or justification, right? Segmentation is selection. Right? What I've shown you so far is what you might call a semantic scale space, right? So the bottom-up segmentation is like generating a scale space, right? So going from coarse to fine. And there are the semantics that we kind of want to pull out of that video feed or image feed or medical image volume that we want to get out of it. Whether or not that is based on learning. Right? So it's a bottom-up method. At the end of the talk, I'll give you an example of ideas here that are based on learning, but this is sort of deep learning aside, if you will. Nevertheless, we'll have to do some selection. Other ways that segmentation is selection. Right? So another way is that we can do selection across feature spaces. When I began to write this talk, I went back to some of my early work in segmentation and tried to interpret it as a segmentation is selection problem. And this was one of the first papers I wrote without my advisor when I was a grad student. And it appeared at ICPR 2004. The basic goal was take an input image, and you want to be able to segment the image into something like this, like the final segmentation, where the checkerboard is one region, the red region is another one, and the purple region is another one. At that time, this was pre even like hog features or sift features, things like that. So we were pretty fundamental or low level in our features. So we could think about color or texture, right? Basically like variance of pixel distributions in local patches or the overall color. And it makes sense to us, the gestalt of this image is that we have 3 segments, 1, 2, 3. Right? But to do that, we have to figure out a way to combine color and texture. Right? So if we only segment on color, we get this segmentation. If we only segment on texture, we get that segmentation. So we had to figure out a way to combine that. So what we actually posed was an energy minimization problem that would choose or select between the feature space at a local level. Right? So in that region, select either color or select texture at a per pixel level. And of course, these were MRFs, so there was sort of smoothness around there. So we wanted to get larger regions that were selecting the same feature space together. And ultimately, we were able to deliver on that in this sort of early work in segmentation from my group. Another type of selection is across time. So I'll give you a discussion about learning from long instructional videos. Right? So in order to do that type of learning, we need to select what frames from the video we should focus on, what groups of frames we should focus on. So that's a selection across time. And finally, I'll give you a presentation, I'll give you a short bit of unpublished work about asking what frames from a video should we select so that we could train a method for supervised segmentation. Okay, so all of these are different interpretations in which segmentation can be viewed as selection. Okay, so here's some work from ICCV 2013 on post hoc guidance on one of these bottom-up semantic scale space hierarchies. So on the bottom here you see the input video, and then you see a coarse level segmentation, a middle level segmentation, and a fine one. So these were the things I was showing you earlier, right? So from bottom to top. Okay. What you see here is the output selection. So the different colors here correspond to what layers of the hierarchy we are going to select from based on the output of an objective function. And what we call the flattening here is saying, well, once we have done that selection, what is one single individual segmentation that we're going to output from that whole hierarchy? Okay, and I will give you, I'll replay the video again because there's other aspects that are in the video that are important here. So we're going to vary how we do that selection and flattening based on different criteria. So initially, we can select based on motion, and we get these outputs. Okay, so the things that are moving rapidly get finer segmentations and are going to get more detail. If we select on humanness, we get these outputs. So there's the head popping out from the back dancer. If we select on objectness, then all of a sudden the background starts popping out, which was not popping out earlier. So what I'm saying here is that we can alter the guidance we want to use to drive the selection in a way that lets us vary the output from that semantic scale space. Okay, and this is the same idea in the tumor case, right? So if we want to know the edema, then we'll select different layers from the hierarchy than if we want to know based on the dead tissue and the live tissue. So how does this work? So this is a method called the uniform entropy slice on motion is at least the motivator for it, the original motivator. All right, so the goal here is, or the driving intuition is that we want to balance the amount of entropy in the different regions that we're selecting across the hierarchy. And what is the entropy over? In this case, for motion, it's over the optical flow, the distribution of optical flow. Okay, so what are we seeing here? So again, these are finer grain segmentations, finer layers of the hierarchy to coarser layers of the hierarchy. The color here you see is maybe the students in the room don't know this color space anymore, but this is the MATLAB jet color space. So red means high, blue means low. Okay, so this means that there's a lot of motion entropy in the larger segments for the girl that's running. This is a girl running through a video. Whereas in the smaller segments, it's going to be a little lower here. The idea is that if we're able to balance the amount of entropy across how we select slices from different layers in motion, this will let us sort of distribute, independent of the size of the selected segments, how much information is in them across the hierarchy, right? So we want to balance the amount of information as we flatten these together. So this is just the equation for entropy over a supervoxel at the ith index at layer L. M is for the magnitude of motion, so we're quantizing the magnitude of motion. And alpha is for the direction of motion. We quantize that to, I think, eight directions. And this is just a standard equation for entropy here. And the idea here is that we're looking to seek a flat segmentation that balances the amount of information, or entropy, those are sort of synonymous in this case, that balances the amount of entropy across the different segments that we're selecting. What's the intuition here, right? So we want to select large background segments for motion because they don't have a lot of information for a static camera undergoing motion, right? So we want to select big background segments in that case, but we want to select small foreground segments because that's where the information is. That's what's actually useful for our processing in this case. So how does the entropy slice work? Okay, so here is a segmentation tree. So all of these bottom-up hierarchies that I'm talking about are formally trees. So that means every node has only one parent. It's not a graph, or it is a graph, but it's a subtype of graph. Okay, it's a hierarchical graph, right? So you have leaf nodes, they have parents, those have parents. Each of those corresponds to one type of segmentation over the volume. Okay, so we call it a slice rather than a cut because it's the sort of the dual of the cut. So a cut is something that cuts edges of a graph into, and separates the nodes into two pieces. A slice is one that selects nodes explicitly on the graph. Okay, so these are plausible segmentation tree slices. Not all slices are plausible ones that we want, right? So we want to know that on every root to leaf path of the tree, one and only one node has been selected. Think about the intuition behind that, right? So if there is no node on a root to leaf path that's selected, that means that those leaf pixels will not be associated with any selected segmentation. Whereas if there are more than one node on a root to leaf path in this slice, that means that we're saying those pixels belong with two different scales of the tree, two different layers of the tree. So we need to figure out a way to enforce that type of constraint. Okay, while at the same time guiding it to balance our criterion, which was a minimization or sort of a minimization of the difference in entropy across different selected segments. Okay, so we can get there based on a binary quadratic program, right? So let's define the terms here. X, okay, X is a vector of binary variables numbering the total number of leaves in the tree. Okay, right? So we can select X. Sorry, it's not the number of leaves in the tree. Total number of nodes in the tree. So this will be leaves as well as internal nodes. So we can select such a node. That means xi is 1. Or we can not select such a node. Xi is 0. Okay? This term here, the binary term, will enforce that balance between selected nodes. So that's what this beta ij term is going to do, kind of give a weight to how much difference there is in our criterion as we're doing that selection. And this alpha I term is capturing the overall sort of magnitude of that node. Right? So in some sense, the linear term is pushing the slice up the hierarchy. It wants a simpler explanation, wants bigger terms. And the quadratic term is the one that's going to sort of balance that out, sort of play against it. Right? So this is like the regularizer, if you will, on the objective. And the linear term is this sort of the data term. Right? Right? So we define this. This is the constraint of interest here. This is what we call the segmentation tree slice constraint. That's going to let us enforce this notion that on every root to leaf path, there's one and only one node that's selected. So how is this interpreted? Right? So what is P? Right? So P is what we call a path matrix. Okay, so every row of P is such a root to leaf path. Okay? Every column of P is one of the nodes in the graph. Okay, so this is the root node. So they're going to be one. It's going to be one for everyone. So the cell is 1 if this node is on this path. Right? So this encodes all the possible nodes of the graph. Here you see the gray path. That's this path here. S0, S2, and S4. S0, S2, and S4, the only ones that are 1. Right? And so X is a binary vector of row, in this case, 6 long. Right? So it'll have X0 through X5. And this is just a p-length vector for paths of 1s. Right? So if we can satisfy this constraint, then we're saying that on every such path, there's one and only one node. If this comes out to be 0, again, that means there's no node on that root to leaf path selected. If this comes out to be 2, that means there were 2 such nodes selected in X. Okay, so this is how we enforce that constraint. In this original paper, the ICCV 13 paper, it's formulated as a binary quadratic program. There's a subsequent work in CVPR, I think 16, which changes this into a binary linear program, actually. So it's a little bit easier to solve. Okay, so how does this work now in practice? Here's another video from a Hollywood movie, the name I'm forgetting. If we instead use classifiers like human detection and car detection, we can have a different notion of entropy, right? So no longer on motion. This is our entropy map, right? So how likely it is that this is a binary entropy now, how likely it is for it to be a human at a certain location. And here are the selections, right? So on humanness, we see very fine segmentations here, and this is the flattened segmentation, so very fine regions on the body. So we're going to be able to focus on that for later processing. Noting that we don't even, if I only showed you this video and I asked you, is there a car in this video, there's no way you could say yes to that, right? So we totally ignore the car. It's not relevant to us. But if we start to look at carness, yes, we may get a human, okay, but it's a bigger human, right? So we don't see much more fine segmentations, but we do start to see the segments popping out in terms of the roof of the car. And so it's sort of doing what we expected or doing what we looked at. Yeah.
What qualifies humanness? How do you extract that from the image?
This is the way this map is computed is basically running a human detector as a sliding window over every location in the video and using the probability of that detection to compute the entropy.
Does it look like for arms, legs, and a head, or?
No. So the specific human detector, this was probably something called a deformable parts model, which has like a texture map of how the human looks as one entity, and then it has a texture map over how like the face looks and the arms look and the legs look, and it combines all that together and gives you a score of the humanness. So this is pre deep learning era, but that's how it works. Yeah. Although in some sense it's just we humans define that structure, and now we just let the deep network learn the structure, right? So yeah.
So for the second one, it is desired. The objective is to detect a car, but we ended up detecting a car and also a human. Is that desirable?
Well, it's not that we detect anything. This is saying, right, so this is a segmentation problem. So if our goal is to sort of find the things we care about through the segmentation, we have the hierarchy as initialization, and then we're just sort of guiding how we interpret that hierarchy for later processing, right? So the more like the key output is that, like in this case, there's no car at all really. We don't really see it, but we are able to sort of focus on that in this one. So we drove the segmentation lower down in the hierarchy for when we were looking at a car, right? But we didn't. Maybe if we had changed the parameters, we could have driven it even further. So the human would have been more with the background, that kind of thing. Yeah, but this is more like interim processing for later processing. Yeah. Other questions? I think these are just doing what I already did. Okay, so some later work that we did in this notion of selecting elements in in this bottom-up segmentation hierarchy, which gets more at your point, is coupling this tree slice problem with an actual video labeling problem, right? So the notion here, so how would you solve a video labeling problem? Well, you would take the graph that I told you about. You'd have a way of assigning data evidence to every label at every node in the graph. And then you'd have a regularization term. You want sort of smoothness over those data labels. This is a classical like MRF or conditional random field type labeling problem. The challenge has always been with those types of problems, how do I draw my neighborhoods around all of the nodes in the graph so I get the right level of resolution so I can enforce continuous labels or smooth labels there. Okay, so if you just use MRF, you only have nearby labels. See, it's not too useful. It forces sort of smooth, low-level labeling. If you try to use the full hierarchy, you get a combinatorial optimization problem that's really hard to solve. So what we did in this work was we iterated the tree slice problem, which flattened the whole hierarchy into one level with a actual CRF labeling problem. Right? So you've seen this already. So this is already in an LP form. And this is just a labeling problem where you have sort of data labeling term over nodes and their possible labels, such as in this case, I think the labels in this case are actors and actions. So cat and running is this lavender color, and I don't know what the purple color actually means in terms of the actual label. Maybe it's nothing. But And this is just your smoothness term here. So why is this useful? So the tree slice problem induces a segmentation at a certain level, right? So that means that we get segmentations out of it, and that also then we use those segmentations to enforce cliques in the graph, right? So every node that's in this segmentation has a new edge that's grown to one another. Okay, and that implies that we want all of those nodes to have the same label in the output. That's what our tree slice is sort of telling us. Then we do the labeling, and then we actually guide the tree slice problem, not on motion or carness or humanness, but on the actual energy. So these terms here of the labeling. And so we iterate these back and forth, and we explore the supervoxel hierarchy, and then finally get a video labeling output, which is something that makes a lot more sense than, say, just looking at the graph for the car. Yeah. So you can play the video once more, so now you know what it means. All right, so early on, we get output that really is what you'd see from a CRF type thing over the supervoxels as the initial graph. But finally, once we converge, we see very fine-grained segmentations, including like the legs of the cat and the head and the ears and so on. Okay, so when this was published, this was sort of state-of-the-art on actor-action segmentation across maybe 7 or 8 actors, cats, dogs, birds, humans, and so on, and actions like running, walking, eating, and so on. Okay, so this is concluding this part of the talk. So this is like the segmentation in the semantic scale space. I can answer any more questions there are about that part before we get to the next part, which is about learning from instructional video and sort of temporal selection. How do we take a long video and select which pieces of that video are most useful to learn about the overall procedure in that video? Okay, so why don't I get there then, right? So this was work that was published last year at AAAI. Okay, so towards automatic learning of procedures from web instructional videos. Right, so why am I interested in, what are and why am I interested in instructional videos? Well, I like video. I like to learn from video. I like methods that learn from video. I personally have learned from video. So I had to remove a fence in my backyard a couple of years ago, and I actually found the right way of doing that on YouTube, which I never would have thought of myself. So I searched for remove fence, and it said the following very obvious but non-obvious thing, I guess. Dig a small hole around each post and fill that hole with water. And then the water loosens the ground and you just lift the posts up. It's like so obvious once you do it. Okay? But before that you probably wouldn't have recognized it. And the other part about it, so I've been working in video and language for a long time and sort of maybe a little bit of QA. So I don't think the problems, just generally, like how do you evaluate the conversion of video into text or into language, right? So that seems like too hard a problem, even though many are working on it and I've worked on it as well. So I think instructional videos are a way of sort of, they're useful and they're a way of making the learning problem more well-defined. So i.e., if you have an agent that's learning to cook, then you can have well-defined criteria such as how good is the dish after the agent makes it, for example, even if the agent's a human, right? Or building something. If they're building a bicycle or repairing a bicycle tire or building an IKEA table, does the table stand? Is a good way of evaluating whether or not they learned how to build it, right? It almost doesn't matter how they do it as long as it works at the end. Or sports, like how well are they able to achieve the sports, right? So my lab is heavily interested in learning from instructional videos and know that humans do this on a regular basis, right? So can we have humans do this? So we've been working on this for a while now. We do focus on cooking because there's a rich amount of cooking videos on YouTube, and the community seems interested in it. And it's a good and hard vision problem, right? So they're very small tools, small objects, fine-grained action. So it presents a good problem. Well, let's call each of these a procedure. And then in any given recipe, you can probably think of it as having some steps of the procedure that have a start time and an end time. You can probably describe each of those steps with some language. The specific words may not matter, but they convey the goals here. And you can call these procedure segments. Okay, so the goal here is take the long video and learn a way to propose plausible procedure segments or select the temporal frames so that we can then go and have an agent that maybe learns what to do in each of those steps. That's the setup here. Okay. So again, the input is a raw video, big T frames. Okay, for training of this problem, we do have human-labeled segments. Okay, so we're only using the boundaries of the segments for this problem, not the textual words, although they're available in the data set. And the output is a set of procedure segments, which are represented as tuples, the time for start and the time for end. Okay, so there are P such tuples, and P is defined as a total maximum number of segments that you can output. So in some sense, the input's going to be something like this, and the output's going to be something like this. Okay, there are many applications of this type of procedure segmentation problem, notwithstanding the learning from instructional video, but also things like video summarization, monitoring, surveillance, and so on. Okay, segmentations that are outputted or selected can be used in downstream tasks such as dense captioning. We had a CVPR paper last year on this. Activity recognition. We have some unpublished work that say if you apply this method that I'll tell you about in a little bit, then you do activity recognition separately in each of the segments and vote on their outputs, you can do better than if you just do activity recognition on the whole video. And visual grounding, we had a BMVC paper on that this year. So we believe in this work, and we're using it a lot for our research right now. How does the framework work? Okay, so the beginning steps here are just a sort of standard feature encoding. So you're going to take your video, has L frames in the whole video, okay, that we're going to uniformly sample, so output L frames, and then we're just going to take your favorite network. We used ResNet. Maybe we can use Tianfu's new grammar-based networks. It almost doesn't matter. We just need a way of converting these frames into a representation-rich vector space that we can operate on. Okay, so we chose ResNet when we were doing it. Okay, then the actual proc nets, or procedure segmentation networks, have 3 steps. 1, to define a context-aware embedding. 2 is to propose possible procedure segments. And then 3, to learn a temporal sequence prediction model that learns how to select among these proposals what are plausible segments to work with. Okay, so I'll just give you one slide each for how these things work. All right, so our context-aware embedding takes as input, right, so this is an L by 512 matrix, 512 because of the ResNet embedding we're using. Okay, 1 for each of the selected L frames, 1 vector here. Okay, and it encodes the context, right? So first thing here is just the raw ResNet feature, the outputted one. Then we define an LSTM that's bidirectional. So it learns a model this way and it learns a model this way. After the output, we take the memory at each layer, sorry, at each step, and concatenate it with the raw feature. So we have 1 original feature, 1 forward LSTM memory feature, and 1 backward LSTM memory feature. So now we have 3, so 3 times 512 is 1536 by L. Right? Why do we do this? I don't believe in magic, because our studies said it was better. Right? So we have this notion of sort of playing Legos in my lab now in the world of deep learning. So we just stitch things together, and we be scientists, and we do experimental analysis, and we choose the one that empirically works the best. In this case, it was this one, period. Okay, so it's a little unfortunate that that's the best we can do right now, but that's the best we can do right now. Okay.
So can you elaborate a little bit what you mean by ResNet features?
Right, so ResNet is just, so one example of a deep network where we kind of, I guess I don't have an example of it.
You actually use the filters as features?
Not the filters. So, all right, so ResNet, VGG, and all these networks are trained to classify, say, among 1,000 classes, right? So we cut off the top layer, and we use the layer just beneath the top layer, and we call that the ResNet feature, or the VGG feature. VGG would be longer than this ResNet feature, but so it's what did that network use as the embedding just prior to its actual softmax layer. Okay, we find, I mean, to be frank, this works everywhere. This is a great feature for a variety of things, both in research and in practice. It's a good thing to do. And even to be clear, I don't think in this work we fine-tuned ResNet, so you can do it without fine-tuning as long as you train on a fair enough data. All right, so excuse me. The next step is to take this L by 15, sorry, this is a typo, L by 1536 context-aware features, and then we manually define possible anchors, essentially locations to begin in time and the length in time to look at. So this is kind of, if you remember like face detection with HAR and AdaBoost, this is like our pool of possible features that we could pull out. Okay, so these are defined by scoping out a plausible set of them. We have many. K is many. K is maybe not much larger than L, but K is larger than L. Okay, these encode length and they encode center offset, and then we can score them based on the values of the features here. Okay, we do max pooling over those features, and these are what provide for us the possible segment candidates. Okay, so it's where they are over the actual video. We just overlay these anchors into the frames, and then we do max pooling to compute their actual score. It's a very simple thing to do, a very sort of standard thing to do, and then we'll get sort of many possible candidates here or proposals. Okay, there's nothing to learn here. There's no parameters of the learning. It's manually defined, and then max pooling on that. Okay, what we actually do learn though is how to use them. Right, so given all the candidates, the third step, the sequence prediction model, given all the candidates, how do we select the most likely sequence? Who are the winners among those possible proposals? Okay. At each time step in this sequence prediction model, and we'll use an LSTM for this, we take as input the current selected segment, decide which candidate segment is most likely to appear next. Right? So the first segment we have is just the no-op, just the beginning of the prediction. After that, every time, we are going to have what was previously selected, and then we're going to select among the other possible candidates. Right? So the proposal vector we have, the location at which it's starting, and then the actual content of it, the actual feature from the context-aware L by 1536 embedding. Okay? So the initial one here is going to be just a start symbol, and then we're going to propose possible candidates from the second stage. We use an LCM for learning the sequence, and it gives us a likelihood of that segment being chosen. Okay, we do beam search over all possible segments in here, and that gives us the first candidate that we're actually choosing. Given that step, we're going to then feed that candidate back into where we just were, so it has like even a higher scale memory, and then apply the same LSTM. And so we're not relying on the LSTM to walk through all of the segments and do one shot like it's A, then B, then C. We just learn a way of saying, given my current segment, what's the next one? So it's kind of like almost like a time invariant sequence predictor model. And then we do kind of the same thing until we're ultimately able to produce many segmentations. Okay, so that's the third step of this, and we believe the LSTM is sort of implicitly learning the temporal dependency among the segments. Okay, so just some segmentations, or some examples I mean. So if you're interested in this problem, so we're working with our data set called uCook2, the second version of a data set of cooking videos that were downloaded or sourced from YouTube. There are about 2,000 of these, roughly 24 per 100 recipes that are uniformly sampled across the globe for popularity and sort of commonality, like their commonality. So there are like a few sushi dishes, a few soup dishes, a few salads. So there's like a good set of interclass and intraclass variance and similarity. And we provide for each of them temporally localized procedure segments, as well as those fine-grained recipe descriptions that are written by humans and checked by humans. So it looks kind of like this. Okay, we don't need to go over these the numerical results are saying that we do well. Okay, that's fine. What we're looking at here more is, oh, do I not have an actual output of it? I do. So let me go to the output first. Okay, so here is a video for making potato pancakes. Okay, what you see here, ground truth, these are what the humans drew when they were doing the segmentation, watching the video, as the steps. Okay, there were 1, 2, 3, 4, 5. The colors are only meaningful in the sense that they delineate the boundaries. They're not meaningful in like this is the chopping stage. Okay, they don't have a label associated with them. And these are what we propose as the output from this learning method. So we actually do a really good job, right? So we in this very cherry-pick select example, right? So we get the first step, which was I think mixing oil or something, or chopping the potatoes. Now we get this one, which is taking the potatoes out of the pot, making them into the pancakes. The next step will be actually, I guess, is mixing some oils and eggs into that, and then the next step is frying each of those selected pancakes into an output, a result that we can eat. And then the human didn't select the last step that we proposed, but if you look at what it is, it's actually frying multiple ones together. So it kind of makes sense that we made that mistake. Okay, but I wanted to go back to this example here. So we were wondering, are we actually learning? Like, is that LSTM learning anything useful? And that's really hard to evaluate because like the results, the numerical results that I skipped over quickly, you can look at the paper, they show we're doing better than every baseline we could find. But is it doing anything? Like, is it just like, is it the resonant feature that's why we're doing well, right? So one thing we tried to get there was to say, okay, if we take our video and split it into two halves, and then we just permute the halves, what happens to our method? Well, this is the original output of the video, and this is after we permuted it. So we've completely failed, right? So the LSTM is just telling us, fine, you got to select something. Every recipe has at least one step, so select one thing. But we don't learn any notion of the sequence. So we see that as a good outcome, right? So it's like what we're looking to find. Okay. Okay, so that's the end of the second of three pieces here. Are there questions about this? When do you normally stop these seminars?
We have 10 to 15 minutes.
Oh, 10 to 15 minutes is perfect timing then. Okay. I can take questions now if you like on the temporal bit here. None of my students actually made any of these recipes for me. It's really unfortunate.
You train them.
I should train them, yeah, tell them. Yeah, in order to get funding for next semester, I need some potato pancakes. Yeah, in fact, I buy them lunch every Thursday. They haven't made any lunch for me. One student made dinner once, actually. But anyway, okay, so the last of the three is another type of selection for segmentation. Okay, so this is, if we're doing that sort of video object segmentation, and it's not just bottom up. If we want to actually say, I want to find this person in the video, how do you do that well? Right? So that problem is called trained or supervised video object segmentation. Okay, we use it in our lab for video manipulation in every terrible sense of that word. We are manipulating the videos for our own benefit. Okay, so it means, for example, I don't know if this is a video. No, there's a video on the next slide. But basically, we have an input video, and we're going to give that input video one mask and say, I care about this thing. It doesn't have a name, doesn't have an object category. It just has a mask at one of the frames. Okay, the state of the art in computer vision in works like this, give it on the first frame of the video clip. So, and it's assumed that there was a human available to give that mask. Right? So why might you want to do this? Right? So, well, I get the mask, I do the segmentation, and then I remove the person from the video, almost like they were never there. Right? So interstate warfare comes to mind. There's lots of reasons why you might want to do this. Okay, so in fact, this is a DARPA project right now called Media Forensics. And so the actual goal of the project is not to do this, but it is to detect when this has been done. Okay. However, my team has the lucky position of being the enemy. So we are the team that's creating these manipulated videos for all of my colleagues. So there's one of us and 12 of them. And they have to tell when we've manipulated the video or not. So it's really fun to be in that position. So we are creating these types of outputs. Okay? There are generally three components to this type of work. Human execution, user-provided annotation. Okay? Then the video object segmentation, which is a well-studied problem in computer vision for maybe the last 5 or 6 years. I think it was created by Kristen Grauman in a paper called Key Segments, maybe ICCV 1314, maybe, roughly around that time. And then finally, the actual removal and the inpainting of the pixels when they're removed. You could also think of taking this person and putting them into another video. That would be another type of manipulation that is being done. Okay? When you have articulated people, it's hard. Okay? How does Hollywood do it? They pay a lot of people to do it very well. Okay? Obviously, we want to try to do it without so many people. So it's much easier to do segmentation on one frame than to do segmentation on many frames. Okay, so here is an actual output from our system. Sorry, actual outputs from our system. Okay, input RGB video. These are ground truth masks. So to evaluate it, the data set we're working with is called Davis. They provide segmentations of the object of interest for every frame. But the training is only on the first frame. Okay. Here is the overlaid segmentation painted pink with the RGB video. And here is the output of our current system. Okay. Obviously, it's not perfect. You can all see when there are, that we've done something, especially in the case of shadows. Okay. But you're mostly smiling. It's a lot better than you think, right? So, this is pretty cool computer vision stuff that's happening right now. Okay, so how does it normally happen? How does the workflow typically happen? Okay, so this is like learning on steroids. Okay, so there are three processes here. First process, you learn your base network on image data, just so that you can tune up your kernels to get to some place in that solution space that it knows what things in natural images look like, right? Then you take that network and you fine-tune it for the specific video object segmentation data set of interest. In this case, it's called Davis. I actually don't know what the acronym Davis stands for, but I didn't make it, so I shouldn't have to know. And this is where you go to, you provide these masks, and you could sort of fine-tune a network that can take in an image, a video frame, and output a segmentation mask, or many such and output many such. Okay, and then finally, the most critical part that we're focusing on today is the third phase, which is you take these networks, or this network that you made, and then you provide it with the one frame of labeling for fine-tuning it for that specific video. Okay, so this is like supervision times 3. You have your base network supervision, you have your offline dataset supervision, and then you have your online individual video supervision. Okay? I apologize on behalf of the video segmentation community for overloading the word supervision 3 times. Okay? But we couldn't think of, I didn't do this, but anyway, it's the state of affairs right now. So I think of this like online supervision. Okay? And this is a framework that has been studied by many people. Okay? In fact, my group doesn't have a listing here. We have not worked and published on Davis in particular yet, really. But nevertheless, given all of this research, what we're asking is, can we do better? Right? So remember, this test network, just by definition of the problem, always selects the first frame. But is the first frame the best one to select? Why should it be the best one to select? Oftentimes, the first frame of a clip, you don't even have the person you care about in it for a real-world application. This video, this example here is not from Davis. It's from the DARPA program. Right? So if we worked in this mindset, we would be failing. Right? We'd rather select something like this frame. So we did the metrics, the analysis. Okay, so here is the number of frames in this short 50-frame video. That's the the horizontal of this performance bar chart. Here, the vertical is the actual segmentation performance. The J plus F is just, it's like a Jacquard versus boundary score. It's just how Davis says to evaluate it, right? So basically it's like a dice coefficient overlapping the actual segmentation you want over the video frames versus the one you provided. But let's be clear here. So each of these bars is the performance over the whole video when trained on this frame or that frame and so on. Okay? We would not have an idea if this was a equal histogram. That would say every frame is the same, the impact on the method. That's not what happens, right? Instead, we see that frame 30 or 29 or whatever that one is would lead to the best overall performance. So let's select that one and train on that one.
So do you know why?
I can show you examples which will make it very clear why. Yeah, just give me a few minutes, right? So, so this one here, so the question is now, sort of, can we learn a method that does that selection just by looking at the video itself? No possible segmentation masks. Because we have, again, we have a human in the loop. They're only available to ask us for us to ask them for one frame. Right? Humans are expensive, much more expensive than running code on a GPU. Right? So we only can ask them one. So we want to learn a method that can ask for one frame. The problem is that actually getting the data to train such a learning method is in itself very expensive. All of Davis has only 4,219 frames. That's only over, I think, 50 or 60 videos. Right? So there's, this is compared to ImageNet, right? 1 million images, blah, 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 right? So there's not a lot of images to train a network. And as we all know, in this era, we still need many examples. So given that constraint, how can we train a model to suggest useful annotation frames? And here's some motivation for your answer, right? So take this example. These are all frames from one video. The object of interest is the car. If I ask you each to, among these 5 frames, which one would you rather start with as your training data, you're all going to answer the same one. And that's this one, right? Because it has the most information about the car in it. Okay, and so that's the quick high-level answer there. Okay, and it extrapolates across all the data I'll show you. Okay, so how do we do this? Well, we go back to computer science first year, your initial data structures and algorithms class, maybe second year, first semester. Bubble sort, right? So we are going to learn a network that does deep bubble sort over a video, assuming all we have for that video are the RGB frames. Okay? So we're not going to directly perform we're not going to propose a network that predicts the performance of a frame. We don't have enough data for that. All we have are roughly 4,219 or exactly 4,219 data frames. Over a number of videos, it's really only going to give us about 50 examples, right? So it's not enough data. Okay? So instead, we're going to learn a network that can predict the relative performance of 2 RGB frames given m random frames of reference. Right? So overall 4,219 frames, we do have their labels. Right? So we're going to generate a large data set that selects, so it's 4,219, choose 2. That's a big number. And then we're going to multiply that with m, where m is 4,219, sort of choose m. M is going to be small, like 3 or 4. And we're going to say if we learn on A or B of those choose 2, A or B, and we choose A, and we compare performance on those 3 or 4 in M, how well do we do versus choosing B? So we just took 4,219 frames and exploded it to the millions. Okay, and then we just trained the network forever on that one. Okay, so it works in that way, right? So we basically have frame A, frame B for a given video. They have to be in the same video. We have other randomly selected video frames from that video. Okay, we're going to use the same ResNet embedding over each of those. I don't actually know. I have to ask Brent if this is the context-aware embedding or just the direct ResNet embedding. I'm not sure about that. And then we are going to basically, we have a very shallow network after that. So it's just 4 fully connected layers that are combining all the information we have here. And that gives us an output which is almost just like a distant distance function. What we really are looking at is what's better, A or B. Right? And that's how BubbleNet works, right? It just takes it, compares pairwise, and bubbles things that are good to the top. It's a simple idea. We believe it to be new. I don't know yet. We haven't done a full literature search, but this will be submitted to CVPR in a bit of time. Okay, how does it perform? This is the first frame. This is the one that we select. Okay, it's not the best, but it's really good. Right? So it does a good job. This is the result of the two segmentation. Given that as the training data, the segmentation, right? So it's quite good. If you only do the first frame, you miss the humans. You mistake them as part of the output. How about this one? This is the first frame performance. This is what we select. Again, it's not perfect, but it's really close to perfect. Okay, so this is the one. It's actually selecting what you would all think of as a good frame to select. Noting, by the way, that Davis in itself is a hard problem because, as a bystander, I would have thought that they wanted to select the motorbike and the driver, but the actual data set is asking only for the driver in this case. Another example. In this case, we do get the best one. I guess in this frame, maybe the dog's not in view or something like that. I'm not sure. Oh, it's the hand. Lovely. Okay, so quantitatively now, how do we perform among other possible ways of doing the selection? So what are the baselines, right? So we can perform first frame, select the first frame. That's what is done in Davis right now. This is the validation set of videos over the whole data set. Okay, if we select the worst possible one, we get a score that's 0.8. If we select the last frame, we get 1.06. First frame, 1.12. Randomly choosing middle frame, like we're just sort of throwing things out, 1.2. If we use deep bubble sort, our method, we get 1.26. Okay, so it's interesting that it's not that different than the middle frame on the data set. Okay, our upper bound, if we were to select the best possible one for every video, it would be 1.4. So we're getting there, pretty close to 1.4. Okay, so and this is the basic idea, right? So we think of bubble nets as a way of ranking over video frames when at training time you have the criteria available, but at testing time you only have the data available. And we've been thinking about other ways of doing this application as well. In fact, you can almost think about ranking different possible networks to use instead of image frames to select, right? So anyway, in summary, I've given you a window into my view of segmentation as selection, right? So across the world of segmentation, across hierarchical or semantic scale spaces, across time, across possible frames to label with a human, different methods of selecting frames for segmentation. Okay, and across all this work, most of the ideas here, they can be defined manually or they can be part of learning. Okay, so if you're interested, all of the code and data for the work, except for those that which is unpublished, is available on my group's website. We do have a requirement in my lab that every work that gets published comes with code that reproduces all of the results in the paper, and it's all there. And I'm grateful for my students as well as the funding sources, which I do not actually list here, unfortunately. But also, before parting, Tianfu mentioned I have a company. We are called Voxel 51. We are making the platform for video understanding. We are 9 people right now and want to be 22 by about 6 months from now, 6 months to a year. So if you're interested, feel free to talk to me or go here to find out what types of positions we are hiring for. So thank you for your attention. I'm happy to answer any questions you may have.
Any question?
So we have been using neural networks for a lot of computer vision tasks recent years. So what's next? So in the CV community, are we going to do it next year, and the year after, or are we going back to the original path that probably we design our algorithm based on the upper bound that those neural networks can provide? So what's your opinion on that?
What's my opinion about what comes next after deep learning? I don't think there is an after deep learning. I don't know. So my view is that, and this is the way I teach it in my computer vision course, so I see deep learning as a way of composing together a rich set of functions that operate over complex high-dimensional data. What is convenient about deep learning is that we have a cohesive underpinning in terms of relatively simple first-year undergrad mathematics and pretty mature hardware and programming languages, right? So you take straightforward ideas in terms of optimization, couple that with software frameworks and hardware implementations, and you find an amazing set of functionality, right? So, but where are the pitfalls in doing that, right? So one major pitfall is we don't really understand why it works. High-dimensional state space is highly nonlinear. We have no idea if we're anywhere near the right answer, even though it performs pretty well in practice. And then on the computer vision side, that's all just general deep learning, right? What makes computer vision not machine learning is a question that is important to keep asking if you're in computer vision, right? So my view is that there's rich structure in the visual world that we somewhat leverage in things like ConvNets and so on, but we don't really actually get at it deeply enough, I think. So what are the constraints in the actual problem domain, like the statistics of natural images, for example, that we should be leveraging so that we could exploit the large amount of data that's available and make learning machines that are quite more adaptable and sort of energy efficient, I guess.
Thank you.
Yeah?
So deep learning is not there yet.
Deep learning is not there yet?
Then, I said.
Not then. Well, I mean...
it's not an end in itself, so there's still a lot to do.
No, deep learning is an enabler. I mean, deep learning is just a new word for multifunction optimization with good hardware and software frameworks, right? So we don't know what's happening, but
to understand it is a problem.
Yeah, we don't understand it, right? And there's some people. There are two camps, I think, if you think about sort of funding programs, right? There are the camps like the explainable AI type camps, which really want to purport to want to understand how to make what's happening in deep learning. Then there are the camps that are like, deep learning's here and we can make an impact. So let's just take the expert out of the loop and figure out how to make deep learning learn on its own. I mean, I agree with both of the trajectories. So I'm not convinced the way we're trying to do explainable AI is the answer. I mean, that's a whole other question, I think. I mean, also, like we had a visit from René Vidal at Michigan, I don't know, like last year sometime. We have a computer vision seminar series, and he gave a really wonderful talk about like the next generation of performance bounds on deep networks. But the actual impact to practice is really low in most of those types of theoretical bounds. So I think there's something missing about the actual way we architect deep networks that doesn't exploit the properties of the problem well enough, like compositionality. Like for example, if I can make you think of things that don't exist just by saying simple words like, on my way over here, we went to get coffee and we passed by a gas station and we saw a pink elephant in the gas station. Right? You all now have this vision of a pink elephant in your head, right? And if I had a GAN, I mean, I haven't done this, so maybe I shouldn't say it right now. I don't think a GAN right now could hallucinate something like a pink elephant, right? But if you go to, this is clearly not the first time I'm saying this. Is there Wi-Fi here?
Yeah. Guest.
Oh, I can just use EDU room. If you go to images.google, come on, and you search for pink elephant, there are tons of them, even actual real-life pink elephants. Right? So I mean, I don't know. There's a lot we're missing, and I think we can get there with better understanding of what actually happens at the nuts and bolts. Other questions?
Talking about that, I mean, in your third part of the presentation, when you were removing the segment which was to be removed, in this place we could see some movement, right? So that is, I guess, because the network is learning what to replace after you are, removing the segment, what to replace it with from the other frames, right?
Yes. Let me just chuckle first. Now I realize this is like being recorded, and so we're going to end the talk with an image of a pink elephant. Here, let me get back to my company's advertisement there. Better. So actually, we don't use GANs for that.
Okay.
So
what I was coming to was that if you use GAN for each frame-by-frame basis, maybe that kind of movement would not be there because it's kind of like making a static frame.
Yeah, maybe we could speculate in that way. I mean, what we use is for that. So our research is not on that type of inpainting. We just use something off the shelf, more of a classical inpainting type method. If you used GAN, so as far as I know, the state of the art in GANs for video is really terrible. We've been doing work. We have a project where we call it video frame inpainting, where you take a long video. It's part of the manipulation world as well. You take a long video, and you want to replace the middle 25 frames with 2 frames. Whatever. Someone walked into the frame, and instead of removing the person, you just want to replace the whole video frame. We tried GANs up and down, left and right, in and out, all these different ways, and we couldn't generate anything that was highly resolved. We have some newer results on it, which are a little better. But I did some digging. There's people dabbling in it. Like Carl Vondrich has some nice work, but it's really it's almost like summary statistics the GAN's able to pick up for video frames. I think we don't have enough data for training, or we don't know how to do it well enough yet. Yeah, so that's why we use for those examples just more off the shelf, classical ideas. Yeah.
Okay. If there's no further question, let's thank Professor Corso again.
Thank you.
Sorry, I won't be able to join you for lunch.